So 85 is where they start the theorems. The first one I kind of already talked about in the previous days. If we have like oh boy, uh, a function like this, how many answers, how many roots should this equation have?
5.
Okay, 4. Unless, what? Right, if you have a double root, that counts as 2. So you could have like 2 normal answers and 1 double root. Or if you have a triple root, that counts as 3. So, just to remind you, a double root might look something like this. So -4 is an answer. It's not really an answer twice. You can only have one -4 answer, but yeah, that would be a double root. Okay. Second theorem basically says if 2 plus 3i is a solution, then 2 minus 3i is going to be a solution. So imaginary solutions always, the conjugate is always a solution also. So they come in doubles. By the way, it could also be like 3i and -3i. That's like 0 plus 3i, 0 minus 3i. So you don't have to have a number up there. It could look like that as well. Okay, and then same thing for irrational answers. You could have, if you have a 2 plus square root of 3 as a root, then 2 minus square root of 3 is a root. Okay, same idea. Basically, it's like you guys know how the quadratic formula has this plus or minus thing. That's kind of where it comes from. The square root is plus, that's also minus. Oh yeah, so this would include like square root of 3, negative square root of 3, kind of like that. So that's like 0 plus square root of 3. So if you have an irrational answer, its conjugate is also an answer, also a solution. You guys remember what the graph of a cubic function usually look like?
Was it a U?
No, that was a x squared makes it
Scribble.
Yeah, it's like something like this. Okay, if you have an odd degree, you have to have at least one real root. Okay, if we have an even degree, like an x squared, it could look like this. So we have no real roots. No x values that make the function equal 0. Okay, but if it's an odd root, because it goes like from down to up or up to down, you have to have at least one solution. Does that make sense? This point on the graph, say it's like 2, 0. That represents a solution to the equation, like maybe it's like this or something. Because this point on the graph means when x is 2, the function equals 0. So that means when you plug in 2, you should get 0. So anyway, if it crosses the x-axis, that represents a root. These would have 2 imaginary roots if it just floats above the graph like this, but an odd degree has to have at least one real. It could be an x to the 5th, has at least one. I might save theorem 5 for later. Yeah, we'll save the rest for later. Okay, we'll talk about the other two. There's 2 more things we need to talk about, but we'll come to it. So page 89 says, tell whether the statements in exercises 1 through 8 are true or false. Justify your answers. Brr. Lydia had hiccups last night. I thought you would know. I felt your pain. Okay, number one, some cubic equations have no real roots. True or false? I just talked about that one. Yeah, all cubic equations should have at least one real root. So, false, comma, how do we know that's true? That was the fourth theorem I read, so we'll just say theorem 4. I should have made you guys read it. That way you'll know where they're at. Whoops. I'm going to help you guys with all these. Number 2, every polynomial equation has at least one real root.
False.
Okay, false. Remember we talked about this, like x squared will have no, if it floats up here, it's going to have no real roots. So false. That's not really a theorem, but you can give a counterexample. Like this equation might be, you guys know what this equation might be called?
Imaginary.
No, like what's the equation? No, like what's an equation for something like this?
Y equals x squared plus 4x minus 2.
Well, it's just plus 1. Just make sure it's up off the graph. So this would have no real solution. It would, on the graph it would look like this. It would just be up 1. And there would be no x value that would make that equal 0. So that's called a counterexample. Show one example that makes it not true. Number 3, the roots of a certain quartic equation. Do you guys know what a quartic equation is?
Yeah.
What?
I'm not going to tell you though.
Does it go up to the fourth power?
Yeah, it's fourth power. Goes cubic
Yeah, it's just-
quartic. Okay, thank you. So it says the roots are plus or minus 1/2, 0, comma, I lost my place, 1 plus I. Is it possible to have, how many roots should a quartic equation have? 4. Is it possible for it to be these 4? Okay, if 1 plus I is a root, what would also be a root?
1 minus I.
1 minus I. So that would make 5 roots. 1, 2, 3, 4, 5. So that would not be possible. So, false. Okay, it violates theorem 1, but I'm just going to say there's too many roots. They didn't explain it that much. Sorry. Alright, number 5. The roots of a certain 5th degree equation are -3, yeah, 4, 1 minus square root 2, plus or minus I. This is basically the same question. Okay, so we have a 5th degree equation. How many roots could it have?
5.
So is this possible? 1, 2, 3, 4, 5?
No.
No.
Because
If 1 minus,
1 plus square root of 2.
yeah. So it's false. I'm not going to explain it all again. 1 plus square root of 2 would also have to be a root. Why did they put 2 in a row? Just because. Okay, number 5. It is possible for the graph of a cubic function to be tangent to the x-axis at x equals -2, 1, and 6. Okay, do you guys remember what tangent means?
almost touching the line.
Not exactly, no.
Touching the line.
Barely touching the line.
Yeah, barely.
Try to shut up.
No, I got it right, but. Good try, Sebastian.
His baby
Where's
is
Sam
out.
at?
Ortho, why not?
Oh, shoot.
I know, Leah did. Troy was young.
Okay, tangent just means that it comes up and brushes it, like barely. So what kind of root makes it a tangent? It's a
Zero.
double root.
Oh, shoot.
So basically,
0 root?
Four.
that implies 3 double roots, right? So what must the degree of the function have to be? At least 6. Okay, there could be some other stuff going on here, but false. We're about to get to the math part. Hold on. Number 6, no polynomial equation can have an odd number of imaginary roots. Can you have an odd number of imaginary roots?
No.
No. Because, like we said, if 3 plus I is a root, 3 minus I is a root, right? So they have to come in doubles. So, was that what they say? No polynomial can have it? That's true. Can't have an odd number of roots. Because basically what theorem said that? Because I should have made you read them. That was the second theorem that said that. Number 7. Suppose p of x is a polynomial with rational coefficients. That just means like fractions, normal stuff. B is rational, but square root of b is irrational. Square root of b is a root of the equation, then negative square root of b is also a root. Okay, well, this theorem only works with normal coefficients like rational. So if square root of b is a root, square root of b is an answer, what else also has to be an answer? Minus square root of b. So that's basically what they're saying. I didn't read the whole theorem. It said you do have to have like normal coefficients. You can't have like square root of 2x. That's a coefficient if I'm on the front. So that is true, and it was theorem 3 that said that. If a plus bi, b is not equal to 0, is a root of the polynomial equation p of x equals 0, then the equation must have an even number of roots. Okay, so they're saying if this is a root, then the equation is going to have an even number of roots. Is that true or false?
True.
So let's say, for example, 3 plus, let's say 2i is a root. Then what else has to be a root?
Negative 2i.
Negative 2i. Well, does that mean like some other number, like 3 can't be a root? No, this could still happen. These come in doubles, but that doesn't mean there can't be another real root over here. If these are roots, these 3 things are roots, then these must be factors of the equation. You guys follow that? Like if 3 is an answer, x minus 3 must be a factor. One of the things that multiplies to get the polynomial. If we FOIL these together, this would be like x squared plus 4. FOIL those. So this will be our counterexample. I'll just say false. This has 2 imaginary and 1 rational root. That is our counterexample. All right, number 9, back to math. Okay. So this next section is talking about the 5th theorem, which I have not mentioned. Okay, the 5th theorem. Let's go look at that together. All right, you guys see where it says theorem 5? Okay, it says for the equation a sub n times x to the n plus a sub n minus 1 times x to the n minus 1. Well, what are they talking about there? They're basically saying this little n just means like if there's 5 terms, this little n would be like the 5th term. And this would be this n would also be the degree of the function. I'll just make one up. Let's do that. Let's say 3x to the 4th minus 2x cubed plus 7x squared minus 4x plus 1. Let's say this is our equation. I just made something up. Okay. A sub n would be like the leading coefficient. It would be the, in this case, it would be, actually it'd be the 15. Yeah, okay. It would be the 4th one. And that's why this is the 4th power. And then this would be like a sub 3. And it's x to the 3rd, and this would represent 7 would represent a sub 2. That's why it's x to the 2, and then this would negative 4 would represent a sub 1, and this is like x to the 1. This one they call, if you look in the formula, they call this one a sub 0. And I guess you could say this is x to the 0 because that doesn't really do anything. So those a's are just the coefficients, the numbers on the front. If you were here yesterday, you remember we talked about possible rational roots are like this, factors of this over factors of that. Remember talking about that yesterday? Okay, so these A's just represent the coefficients in front. Okay, they called it n minus 1. So it just does a countdown. You just, whatever the first one is, the next one is just one lower. This is not a power, this is just a way of counting, like the fourth A, the third A, the second A. So, okay, I'm not going to spend it's not that important, I'm not going to spend a ton of time on it, but if you look right below that formula, it says the sum of the roots is negative a sub n minus 1 over a sub n. Well, what's the a sub n minus 1 stand for? Stands for the second coefficient. Right? That's what it says. So we're going to use the second coefficient over the first coefficient, a sub n. So in my example, it would be negative 2 over 3, which 2 negatives makes a positive. Okay, this is a trick somebody figured out. Even though I don't know what the roots of this are yet, I don't know what the answers are yet, it turns out that if you add all the answers together, all the roots together, it would be negative this thing over that thing. I have no idea how they figured that out, but they did. Never seen the proof. Okay, and then it says the product of the roots is a sub 0 over a sub n, if n is even, or it's negative a sub 0 over a sub n, if n is odd. So n basically represents the degree of the polynomial. So in my example, since it's even, I could find the product of the roots by using this little formula right here. What does a sub 0 represent? The last coefficient, kind of like we used yesterday. What does a sub n represent? It's the first coefficient. So in my example, it would just be 1 over 3. Okay, so this was the sum of roots. I just used this little formula that gave you the second coefficient over the first coefficient, negative. And then this one was the product of the roots. Clear as mud? Okay, really it's not that hard to do. Okay, so number 9, we'll do a couple examples, you guys will get it. You just have to plug the numbers into the equation, the formula. It says find the sum and the product of the roots of the given equation. So we're not solving to find the roots, we're just supposed to figure out what the sum is, what the product is. So the first one is find the sum. So what formula do we use for that? This one. Which means use negative second coefficient over first coefficient. Okay, what's the second coefficient on number 9? Negative 3. Okay, see where you got that? What's the first coefficient on number 9? 4. So it's negative 3 over 4, which is 3/4. Okay, and then the product of the roots. Now, is this degree of number 9, is it an odd or even degree on number 9? Even. It's an x squared. It's an even degree. So that means we're using this version instead of the slightly different this version. So what did a sub 0 stand for? Last coefficient, first coefficient. Yeah, so the last coefficient is 6, the first coefficient is 4, and that reduces, always reduce to 3 over 2. So those would be our two answers. Okay, before I forget, man, they made 10 and 12 tricky. Let's do 11 first, and then I'll go back and talk about. There's a trick on 10 and 12. Okay, so we need the sum of the roots. You guys remember the formula? It's the second coefficient over the first coefficient with the negative in front. So on 11, what's the second coefficient? 5. What's the first coefficient? So it's just negative 5/3. Comma. So is the degree odd or even on number 11? Odd. So that means we need to put the negative in front on this one. So we're going to do last coefficient over first coefficient with the negative. So what's the last coefficient on number 11? Negative 2. Yeah, if there's a negative and minus in front of it, make negative. What's the first coefficient? 3. So it's negative 2/3, which is just 2/3. Okay, so on number 10, the tricky part is what is the last coefficient? Kind of, it's a trick question, yeah. It's a 0. Why is it a 0? Yeah, like number 9 had a +6, or number 11 had a -2 at the end. Number 10 does not have a constant at the end. So its last coefficient is actually a 0. Same thing on number 12, except for, well, okay, number 12, what's its first coefficient? 1. Because there's just a 1 on the front. What's its last coefficient?
0.
No.
5.
No.
-5.
-5. Why is it -5? Because the 5 is on the wrong side. You got to subtract it over so it looks right. Standard form. Okay, on 12, what is its second coefficient?
0.
Yes. Why is it 0? Because there's no x cubed. Yeah. Kind of like when we do synthetic division. You know how we put zeros in there if they're missing a term? All right. Okay. Yeah, we need to finish this. Finish him. By the way, we're going to have a test on Tuesday. We could finish it tomorrow. Since today's Wednesday anyway. Alright, why don't you guys do 10 and 12? Real quick. That's for you, Sebastian. Sam, if you're watching, go ahead and do it, all of it.